In this session we will learn how to draw cam profile for radial roller follower moving with simple harmonic motion during ascent and uniform acceleration and retardation during return stroke. So this is the problem statement. Follower type is radial roller follower. Minimum cam radius is 25 millimeters, which will be the radius of base circle. Stroke length of follower is 30 millimeters. Roller radius is 7.5 millimeter. And during rise of the follower, cam rotates with angle of 120 degree. We call it as outstroke angle theta O. And during outstroke, follower moves with simple harmonic motion. Outstroke is followed by dwell period of 30 degrees, which is in turn followed by return stroke, during which cam rotates with 150 degrees and the follower motion is uniform acceleration and retardation. And during the return stroke, while the follower moves with uniform acceleration and retardation, acceleration period is half of the retardation period. So this is important condition. So the first step is to draw the displacement diagram. On y-axis we plot the stroke of follower and on x-axis we plot the cam rotation angle theta. So lift of follower is 30 millimeters. So for y-axis we will take scale of 1:1 and plot the lift of 30 millimeters. So this is the lift of 30 millimeters. I have drawn one horizontal line through that point. So this is the total lift of 30 millimeters. I have plotted it on the y-axis using scale of 1:1. Now we divide the x-axis into three segments. First, for outstroke angle, which is 120 degrees, we take the scale of 1 centimeter equals to 20 degrees for outstroke angle. So 6 centimeter will give 120 degrees. So this is the outstroke angle using scale of 1 centimeter equals to 20 degrees. So 6 centimeters, 120 degree. Next, let us mark the outstroke. So this is theta O, 120 degrees equals to 6 centimeters. The next is dwell period of 30 degrees. Dwell period of 30 degrees. So for that, I have used a scale of 1 centimeter equals to 15 degrees. So 2 centimeter will give 30 degrees. So this is dwell period theta D. And this dwell period is followed by a return stroke, during which cam rotates 150 degrees. Now for return stroke, I have taken scale of 1 centimeter equals to 15 degrees. So 6 centimeter will give 150 degrees. So this is the return stroke angle theta R, 150 degrees, 6 centimeters. Now we divide the outstroke angle and return stroke angle into 6 equal segments. So outstroke angle is 6 centimeters representing 120 degrees. So I will divide it into 6 equal parts. So one division of 1 centimeter. So 1, 2, 3, 4, 5 and 6. I will number those divisions starting from the origin. Okay. So this is 0, 1, 2, 3, 4, 5 and 6. I will draw the vertical lines parallel to the y-axis through these divisions. So this is first one. This is division number 1. Now similarly, we will divide the return stroke angle into 6 equal parts. So return stroke angle is 6 centimeters representing 150 degrees. So I will get 1 centimeter for each division. So let us number these divisions. So this is dwell period. So start of dwell is 6, end of dwell will also be 6. Then 7, 8, 9, 10, 11 and 12. Now I will draw the vertical lines parallel to the y-axis passing through these division numbers. So this is division number 11 and this is 7. So we have divided the outstroke and return stroke angle into 6 equal divisions each. Now outstroke is with SHM. So we draw a semi-harmonic circle on the y-axis with its diameter equals to the lift of the follower. So this is the semi-harmonic circle. Whose diameter is equals to the lift of the follower. Now outstroke is with SHM. We have drawn the semi-harmonic circle. We have divided the outstroke angle into 6 equal parts. So we will divide this semi-harmonic circle into same number of parts. Okay. So 180 divided by 6. So each division will be of 30 degrees. So let us mark the points. So 1, 60, 90. Okay, and from this side 30, 60 and 90. So this is one division. This is another one. This is 90 degrees. This is 60 and this is 30. So we'll number these divisions from bottom to top because the follower is rising during outward stroke. So here is 0, this is 1, 2, 3, 4, 5 and 6. Now I will join these divisions to the center of the circle, semi-harmonic circle. So this is division number 5, division number 4, division number 3, division number 2 and division number 1. Now let us project these divisions on semi-harmonic circle across the divisions of the outstroke angle by drawing the lines parallel to the x-axis. So line coming from 1 will intersect the division line number 1. So projection line number 1 will intersect division line number 1 at 1 dash. Line number 2 will intersect division line number 2 at 2 dash. 3 will intersect 3 at 3 dash. 4 will intersect 4 at 4 dash. 5 will intersect 5 at 5 dash and 6 at 6 dash. So let us number these divisions. So 1, 1 at 1 dash, projection line number 2 and division line number 2 will intersect at 2 dash. Projection line number 3 and division line number 3 will intersect at 3 dash. Line number 4 and division line number 4 at 4 dash. Projection line number 5 with division line number 5 at 5 dash and projection line number 6 with division line number 6 at 6 dash. Next we draw a smooth freehand curve passing through these intersecting points, and that will represent the displacement diagram of the follower during outstroke when it is moving with simple harmonic motion. Now next period is dwell period of 30 degrees during which the follower is at rest at the topmost position. So 0 displacement of the follower will give a straight line during dwell period, and 6, this is 6 dash. Okay. Now return stroke takes place with uniform acceleration and retardation, and for that acceleration period is half of the retardation period. So we need to find out the boundary where the acceleration ends and retardation starts. So we know that x-axis also represents the time. So here it is mentioned that acceleration period is half of the retardation period. So let us suppose that theta r1 is the angle turned by the cam during acceleration period of the follower, and theta r2 is the angle turned during retardation period, and theta r is the total angle turned during return stroke. Now it is given that acceleration period is half of the retardation period. So here we can write acceleration period theta r1 is half of the retardation period theta r2 plus theta r2 equals to theta r. This will give 3/2 theta r2 equals to theta r, and so theta r2 is equals to 2/3 of the total return stroke angle, which is equals to 2/3 into return stroke angle is 150 degrees. So theta r2, angle turned by the cam during the period when follower retards, is 100 degrees. Total angle is 150. So angle turned by the cam during acceleration period is 50 degrees. Okay. So we divide. Let me write it down here. Theta r1 is 50 and theta r2 is 100. So we'll divide this period. Total is 150 degree. 1 centimeter is 25 degrees for return stroke. So 25 plus 25 will be 50. So this is my theta r1 and this is theta r2, which is 100. Okay, 25 plus 25 50, 25 plus 25 plus 25 plus 25 is 100. So this is the angle turned by the cam during which the follower is accelerating, and this is the angle turned by the cam during which the follower is retarding. Now we divide this line number 8, which is the boundary of acceleration and retardation period, into same number of divisions as that of the return stroke angle. So we have divided the return stroke angle into 6 equal divisions. So we will divide line number 8 into 6 equal divisions. Total is 30 millimeters. So each division will be of 5 millimeters. So this is 1, 2, 3, 4, 5 and 6. Let us number these divisions from top to the bottom, because this is the return stroke. Follower will return to its lowermost position. So this is 6, this is 7, 8, 9, 10, 11 and this is 12. This one is 6. Okay. Now we will find out the displacement of the follower during the acceleration period and during the retardation period. So now we have V equals to U plus AT, right? Now during acceleration, say this is the topmost position and this is the lowermost position. Follower starts to return from topmost to the lowermost position, and when it starts from topmost position, it is accelerating for some period of time, and after that it is retarding. Okay. During the start of the return stroke or during the start of the acceleration, initial velocity of the follower was 0, and at the end of the acceleration it will gain some velocity equals to V, and at the end of the retardation final velocity will be 0. So during acceleration, if you apply this equation, V is equals to initial velocity is 0, so 0 plus F1 is the acceleration and T1 is the time required for acceleration. So from this we get T1 is equals to V upon F1. Call this as equation number 1. Now during retardation, if I apply the same equation, final velocity is 0, okay, is equals to initial velocity is V. Now it is retardation, so minus F2 is the magnitude of retardation and T2 is the time required during the retardation period. So we get T2 is equals to V upon F2. Call this as equation number 2. Now if we equate these two equations, so I will convert this. Acceleration period is half of the retardation period. So for T2 I can write it is equals to twice T1. So V upon F2. So T1 is equals to V upon twice F2, and that is also equals to V upon F1. By solving this equation, this goes. So what we get, F1 is 2 times F2. Okay, so acceleration is 2 times the retardation. Now to find out the displacement, we'll use the equation S is equals to ut plus half at square. So during acceleration, say displacement of follower is S1, which is equals to initial velocity 0 during acceleration period. So half acceleration times square. Now we have F1 equals to twice F2. So we'll substitute that S1 is equals to half. F1 is twice F2. So twice F2 T1 square. Okay. So S1 is equals to F2 T1 square. Now during retardation, say displacement is S2, initial velocity is V. So V, it is retardation, so minus half of F2 T2 square. F2 is the magnitude of retardation. So here is T2. So this is equals to, now going back to this equation, V is equals to T2 into F2. So F2 T2 square minus 1 half F2 T2 square. So F2 T2 square minus 1 half F2 T2 square will give 1 half F2 T2 square. So now we have 1 half F2. T2 is twice T1 because acceleration period is half of the retardation period. So T2 is twice T1 square. So this gives us 1 by 2 F2 4 T1 square. So this is equals to twice F2 T1 square, and we have F2 T1 square is S1. So this is equals to twice S1. That means S2 is twice S1. Next we have S1 plus S2 is equals to S. Total displacement during return stroke. So S1 plus twice S1 equals to S. So we get 3 times S1 is S, and therefore displacement of the follower during acceleration period is 1, 3, the total displacement. So we get total displacement is 30 millimeters. So S1 is 10 millimeters, and so S2 is 30 minus 10 is 20 millimeters. So I will write down here S1 is 10 millimeters and S2 is 20 millimeters. So let us plot this displacement on y-axis. So we have divided this 30 millimeters into 6 equal parts. So each division is of 5 millimeters. So S1 is 10. So 5 plus 5, 10. So this is the end of acceleration period. So this is S1, which is 10, and this is S2, which is 20. 5 plus 5 plus 5 plus 5, 20. Now let us draw the projection lines. So we'll draw the projection lines from this corner because this is return stroke 6 dash. Line number 7 will intersect division line number 7 at 7 dash. Now line number 8 will go to this, will intersect 8 at 8 dash. Now this is the end of acceleration period. Now retardation period from this corner. Line number 9 will intersect 9 at 9 dash. 10 will intersect 10 at 10 dash. And this line number 11 will intersect 11 at 11 dash. The next we draw a smooth freehand curve passing through all these intersecting points in order to get the displacement diagram during return stroke. So this is 7 dash, 8 dash, 9, 10, 11 and 12 dash. So this is the displacement diagram of the follower during return stroke when it is moving with uniform acceleration and retardation, and acceleration period is half of the retardation period. The next we'll draw the cam profile. So first step is to draw the base circle. Radius of base circle is 25 millimeters. So this is 25. Next step is to draw the prime circle. Now prime circle radius is equals to base circle radius plus roller radius. So 25 plus 7.5 we get 32.5. Right? So for prime circle, whose radius is 32.5, so this is 32.5. Okay, with the same center we draw the prime circle. Now let us draw the axis of this cam. And since the follower is radial, the axis of motion of follower or line of action of follower will pass through the cam center, which is here. Now let us draw the roller in its lowermost position. Radius of roller is 7.5. So of course its center will lie on the prime circle. So it is really too small. We will draw the roller. So this is the position of the roller at the when the follower is at lowermost position. Okay, this is sufficient. Now we join the cam center O with the roller center 0 using a straight line, and this will be the reference for dividing the prime circle. Now we divide the prime circle into same number of segments as done in the displacement diagram. With the x-axis, we have divided the x-axis into 3 segments. First one is 120 degrees outstroke. So let us plot that angle. So it is 120 not 60. So this is wrong. So total is 120 degree outstroke. So this is theta O outstroke angle. Next is dwell period of 30. So this is dwell period of 30. The next is return stroke of 150 degrees. So 0, 10, 30, 60, 90, 100, and here is 150. This is theta D, and last one is theta R, and last is the remaining 12. Now we have assumed that the cam rotates in clockwise direction, so I have divided the prime circle in counterclockwise sense. Okay, that is important. You have to divide the prime circle in the direction opposite to the direction of rotation of cam. Now in displacement diagram we have divided the outstroke angle into 6 equal parts. So here we will divide the outstroke angle into same number of parts. So 120 divided by 6 is 20 degrees. So each division will be of 20 degrees. So let us go first 20, 40, 60, 80, 100 and 120. Let us mark these divisions on the prime circle. So this is one at 20 degrees, second at 40 degrees, this is third at 60, this is fourth 90, 80, and this is at 100, and then last one. We'll number these divisions starting from 0. 0 is the center of roller. So this is 1, this is 2, 3, 4, 5 and 6. End of dwell is also 6. Now we'll divide the return stroke angle into same number of parts as done in the displacement diagram. We have divided the return stroke angle into 6 equal parts. So 150 divided by 6 is 25. So each division will be of 25 degrees. So this is 25, 50, 75, and then now this is okay, 25, 25, 25. Now we'll come from this side. So 10, 20, 25. Okay, this is 25. So 1, 2, 3, 4, 5, 6. Now we'll mark the divisions on the prime circle. Okay, 120 plus 30, 150. This is first one. So we'll number these divisions 6, 7, 8, 9, 10, 11, and this one is 12. Now we'll mark the displacement at all these instances, instant number 1 to 12 from the displacement diagram. Okay. So let us measure the displacements. At instance number 1, displacement is 1 to 1 dash and it is 3 millimeters. So first of all, we'll draw the line of action of the follower at all these instances. Radial follower, so all the lines will pass through the division numbers and the center of cam. Repeat the same procedure for return stroke. This is because the follower is radial. Line of action of the follower at all the instances must pass through the center of the cam. Now at instant number 1 it is 3 millimeter displacement, 1 to 1 dash. So we'll plot that. So it is 3 millimeters. So this is 1 dash, 1 to 1 dash. Now at instant number 2 the displacement is 7.5. So it is 7.5. So 2 to 2 dash is this 2 to 2 dash. Now at instance number 3 the displacement is this much. I will plot it on instance number 3. We'll name this point as 3 dash. Now at instance number 4 displacement is this much. So we'll plot it here. At instance number 5 displacement is this much. So this is 5 to 5 dash, and at instant number 6 it is 30 millimeters. We plot the displacement beyond the prime circle on the line of actions. So this is 6 dash. At the end of dwell 30 millimeters, 6 dash. Now at instance number 7 we measure the displacement. We plot it beyond the prime circle on this corresponding line of action. So this is 7 dash. And then we will go for 8 and 9 up to 12. So this is 7 dash. Now at instance number 8 this is the displacement. So this is 8 dash. Similarly we plot for 9 and 10. At instance number 9 it is 11 millimeters. So this is 9 dash. Now at instance number 10 it is 5 millimeters. And at instance number 11 it is 2 millimeters. This is 11 dash. And 12 it is 0. Now these are the positions of the trace point. This one center of roller. So at all these instances we will draw the roller having radius of 7.5 millimeters. So this is the radius of roller. Instance number 1. This first roller. So we draw the roller at all the instances. Instance number 2. Then number. So after drawing the roller at all the instances with these positions of trace point at the centers, the last step is to draw a smooth freehand curve tangent to all these circular arc of rollers. We start from this point and this during dwell period, and here the last dwell will be the perfect circular arc. So we join this. So the cam profile for roller followers or all the followers during the dwell period, the cam profile is the circular arc. So we draw this curve using a rounder. Okay, this one and this one are the circular arcs during dwell period. So this is the cam profile. Thank you.